ahead.
Yeah, okay, I'm going ahead. Thank you very much. Like Sam said, thank you very much for being here today. It's really amazing. It's particularly amazing because we just a couple of weeks ago, 2 weeks ago, launched mainnet for Aptos. So I'm really happy that I can talk a little bit more about the work we did before. As you can imagine, when we walked towards mainnet, we were really busy to get it done, and now we are very happy that it's working, and I want to report a little bit about this. Okay, so Aptos is a new layer 1 blockchain, which has basically the properties to be safe, which is because of Move, and we will talk a little bit more why Move makes us safe. So it's basically some of the stuff I will tell you is quite the same like Sam told you, which is natural because we share the same language, but there will be also some aspects which you might not have heard about the safety of Move. It's fast because we do block software transactional memory, which allows us parallel execution in a basically optimistic way. And we have some numbers which shows that it can get very fast. The difference of block STM to something like Solana or SwiMove is that you do not need to specify the data dependencies. Basically, the data dependencies are automatically figured out during execution. And some of the ideas, by the way, that Sam mentioned about charging actually for contention, that's a quite interesting idea, can be also probably done for block STM. It's reliable because we use proof of stake, and it's also the way of using proof of stake which makes this blockchain reliable, is at least our intention and the design, the way how we designed it. I will not actually talk about these details here because this is more about the protocol and the setup of the blockchain and not about Move, but just to mention that. And it's decentralized because it has autonomous governance. I will talk a little bit about this. So again, like, so we have as basic architecture components, classic Move, how I call it. Sam called it DM Move. I call it classic Move because it's containing a lot of concepts which derivations of Move like SwiMove do not contain, like being able to basically access via addresses global storage, which is also a rather flexible way for programming, but indeed also has some issues like Sam nicely showed. This is example of the cool assets there. And we have flexible key management in Aptos, which means you can create your own hybrid authorization options. So basically governance and voting and this kind of things are a special instance of this custodial hybrid key management options, and we will see a little bit more about that. Like I said, there is a high throughput. It's not only because of the parallel block STM execution, it's also because of the pipelined architecture. And last but not least, so we actually want the blockchain to be live and living and evolving. So we have paid some attention on how you can actually upgrade code instead of EVM, where basically once you deploy your contract, it's immutable, and then you have to build a proxy and other dangerous things. We have thought about a code upgrade, and it's part of the blockchain. So the Aptos network, I don't really need to tell a lot about this because I think you understand what blockchains are. There is a validator set, there are full nodes, there are light clients, which might be similar like the sparse clients, which Sam was talking about. And those things play together in the usual way. And before I go into the detail, I want to tell you a little bit more about who we are. So it's interesting, like, you know, once we launched Aptos, we got some remarks. Hey, you have stolen what your work is stolen from DM. That's kind of a little bit crazy because we are kind of the original creators of DM, similar like Miston. So the history which we are looking at is that there was one team at Meta that's working on the DM, formerly Libra blockchain, and part of those people went into the Aptos startup, and part of those people went into the Miston startup. Today at Aptos, we have a number of people working on the Move team. Those which are red colored here are those which actually will also give presentations on this event here. And yeah, so Victor, Wolfgang, Junkiel, Dario, Tang, and Ranchen were all part of the original move team at Meta. Okay, I want to point out that when we talk about move, this is, and Sam did the same thing, pointing out that this is really a collaborative work between multiple people. It's not like move would be invented or created by one person. It's a community project which is together evolved by multiple people. There are stakeholders involved from Starcoin at Zolstar, from SWE or Miston at SAM, from Aptos it's me. And we are actually actively working. We have weekly meetings, design discussions, we have Discord and everything. No? So it's a relative friendly environment in which we are trying to evolve the move language in a way which is beneficial for each one, for every of the blockchains which are using move. And as Sam was saying, so we think this is essential, no? Because if you build some technology which is based on move, like you build some program analysis, you build some auditing expertise or anything like this, we understand that you don't want to be locked into one particular blockchain. You want to be able to apply this technology across multiple blockchains. And that's what we are also totally committed to at Aptos. Okay, so now I may be a little bit repetitive, repeating what Sam also said, but it's maybe my personal viewpoint. Why did move even exist? And why do you create a new smart contract language? So I have worked for a long time at Google, by the way, and it was absolutely nothing you could do at Google. Creating a new language was not what you should do. There is this exception of Go, as you probably know, but the advice was never even use a new language. So why did we do it? No? So there was basically the argument already brought up that existing smart contract languages like Solidity may be easy to use, but are not easy to safely use. So this is a big concern. The main problem is basically dynamic dispatch and the possibility to call into code which you don't know. But also the data ownership model is a little bit broken in our opinion. No? So Solidity is not really the right thing to, we thought at DM and at Libra to write smart contract languages, to write smart contracts. And existing program languages would be another option, and then using something like WASM or so, for example, to implement them or to execute them. The problem here is determinism. For example, you need the deterministic language and the deterministic framework and library for being able to execute smart contracts. But the even deeper problem is metering or gas. So how do you add this to an existing language? You really need to basically modify and extend the compiler in a significant way. And then there is the sandboxing. Okay, you can deal with the sandboxing, maybe with WASM, that's possible. But there is a last thing here, which is maybe the most important one. So we want smart contract languages to be simple, both for understanding of humans, but also for reasoning formally, like for example, with a move prover. And if you take a language like Rust, which has a lot of nice properties and would be maybe the ideal choice, you could think for smart contracts, it's definitely not a simple language. No? So that was a further important reason why Move was created. And I won't hide it from you. Last but not least, the reason was because it could be done, no? Because it was Meta, and Meta thought we can define a new language, so it was simply done. And that's why we are here today. And what are the design goals of Move? Again, it might be a little bit repeating what was already happening, but a different view. So very important is the data safety via a modern ownership model of data. No? There is a modular encapsulation, so that, like we already heard, that basically only the module which defines the data type can access a module, and it is on behalf of the module, or the module can basically expose APIs to see parts or more or less of this data, but it totally has control over what is visible and accessible from the data it defines. No? And in addition to that, modular encapsulation becomes the Bohr semantics from Rust, which allows you to clearly reason about references to data, the lifetime of references, mutation of data, and things like this. And together with that comes the linear types, which are very much related to Bohr semantics. So this is a modern way of dealing with ownership. But the difference to Rust is simplicity over sophistication. No? So restrict the language to basic concepts, make an order of magnitude simpler than Rust. So this is one set of goals. Another set of goals, which is also equally important, the language is supposed to be based on a bytecode virtual machine, which is fully typed. That is different to the EVM. If you know the EVM or even WASM, it's basically a machine code, no, without any relevant typing system. The only types which exist there are integers. But in the case of move, the bytecode is fully typed. So you can basically take move bytecode and translate it back to readable source code. Now, there is no real information lost. And this makes it possible to verify the correctness of the bytecode at runtime and don't depend on the correctness of a compiler. This is very important. Similar, which comes as an effect of this, is well-defined formal semantics, which you get over the bytecode. Because the bytecode is small and basically the essence of the semantics of the language, you can define it, you can formalize it, you can write tools like the move prover and other analysis tools which work on this bytecode effectively. So that's another two important goals. Then last not least, so that was also mentioned today, so the language can be instantiated for different protocols and even different programming models like we have seen. This has been called also like a schema language. Schema language is a language that is not defined for a particular application, but can be instantiated for those applications. And even though Move wasn't really originally designed to be like this, it turned out to be working in this way. Basically also because there are no built-in things like block height or whatever kind of information from the blockchain. Everything goes over framework, so you can define whatever you want to do. You can have a quite different programming model like SAM represented for SWI, or you can do the more classic move model like cont, ZOL, and Aptos using. And last not least, so the language has the potential to run really fast. This is something which may not be that obvious, but actually, as a compiler constructor, I can tell you, if you take move, you could compile it as fast as C. There's really nothing which stops you from that. And that might be important down the road when we are basically hitting bottlenecks by computation and not longer by consensus or network or storage system, which is more or less something we should expect, because it always happens in computer science that eventually the peripheral things like storage and so on become cheaper and cheaper. And then you need to basically catch up on the actual computation power to really exploit these new possibilities. Okay, so I will talk about Aptos Move now, and I don't know how many people acquainted to Move are here. I guess there are quite a number. So some of the things you might know already, but basically it's also an introduction into Move if you want so. And let's see what we have. So first, let's start with a classic Move storage model. So that's what we also have in Aptos. Data is stored on an account address. In Aptos, we have chosen to use 256 bits for this to be sure we don't run out of space, so to say. And under each account, you find now data which is basically indexed for that account by the type. And the types can be parameterized. This is very important. So like if you look at this diagram, you see there are three accounts. One just contains data structure called account, which is the information about this account. The other contains account plus a balance for a particular currency, which would be Apt, our own token. And then there is another account which contains a balance for ETH. And this can be done using the same balance code by type instantiation, which is a pretty idiomatic way to work with Move. That looks then like this. Pretty simple example. So you define this structure, this module balance, which contains this data type balance, and which in turn has a coin, which comes from somewhere else. And then you can create this. You move to basically this data structure into this memory slot. And indeed there would be more functions on balance, which I haven't mentioned here. Now, if you want to create actually a particular instance of this balance, then you would just define an empty type like this APT type. It's a kind of a marker type. It's also called in Rust and other languages. and you instantiate the balance when you create it with this type, and then now you have a balance for apt. Okay, so interesting is the code model for moves. This is a little bit different than in other smart contract languages. Well, the same thing is, it's not only data, but also code is stored on an account and address. So that's the same like in Ethereum. However, what is different is that the code stored under one account manages data which is owned by other accounts. So we basically decouple the management and the ownership of data. Now you can see this in this diagram. We have this module balance, and it manages the balances of multiple other accounts. That is quite different than in Solidity, if you know it, where basically the data is owned by the same account, which also contains the contract code. And we think this is a very important property of Move, which makes it possible to program certain things in a much nicer and more intuitive way. However, we also know, and that was the problem with classic Move, that there are situations where this doesn't work out, where you really have a different kind of constellation. That particularly happens with NFTs, where you actually need one account to own a large amount of data, like you do by default in Solidity. And this is one extension in Aptos Move. We added the table type into Aptos Move, which is not like you would think a hash map. It's really a storage table. It's basically unlimited or limited only by the amount of gas you like to pay for it, and allows you to manage large collections. We do not allow to iterate you over tables. That is pretty much the same like in Solidity, but you can imagine that contract function is called with a particular key in the table and then just works on that key, and then it's another time called with another key. So there is not necessarily a need for iterating this kind of tables. Okay, so I want to talk a little bit about the general model of transaction authorization, because I need that also for talking about some other things. Transaction is basically executed by calling an anti-point function in a module on chain. We have seen this also before in SwiMoves. This is pretty much the same, but there is also another way how you can execute a transaction. That's important for various things. So where you basically write a so-called script. So the script is a one-time contract, if you want so, which is only uploaded for this particular execution where it's used, and then it's forgotten. So it's not stored on chain. This is quite handy, for example, for larger batch operations or so, which you want to perform on chain without the need to deploy some code. And users can execute scripts on our chain. So both script and anti-point transactions have from the parameters the same kind of design. So they take one or more signers as parameters. The signers are basically the authorization tokens for specific accounts. So behind each signer is an address of this account. And we haven't touched that, but in Move, the restriction is that you can only move to or publish data to an address if you have an assigner for that address. But there is more to a signer. It's not only this publishing. The signer is typically used to implement access control, to implement capabilities and other forms of access. It's basically the basic access control model, which tells you, aha, this is this account, basically the authorization or the authentication, but not yet the authorization, which you then implement in your own smart contract logic. And you can have many derived authorization schemes built on top of signers. You can do assertion-based access control, like we did mostly in DM. You can do capabilities or object capability-based design, which is a very nice way to do it. You can do, as we will later talk about governance, or where a signer is basically not producible by a single owner, but needs to be a vote there for multiple people to actually create that signer. So it's a quite flexible tool, the signer. That brings me now to the next point, to autonomous accounts, which is one of the features Aptos Move has. You can think about an Aptos autonomous account simply like an account you create, and after you create it, you forget the key. So no one externally to the blockchain can create a signer for this autonomous account any longer. Now you can ask, okay, so if I can't create a signer anymore, how can I authorize any operations on this account? Well, that is now governed by contract logic, which the contract around the autonomous account will have to implement. No? So as I said before, multiple different custodian auth models, which you can put on it. You can imagine you do like multi-signing in the sense there need to be 5 transactions or 5 stakeholders before the signer capability, which allows you to access the signer for this autonomous account, can be produced by the contract code. You can imagine there is a voting mechanism like we have basically in the Aptos blockchain itself, where there need to be an on-chain voting with 50% or more before the signer can produce. You can be implementing whatever scheme you want. And as I said, so the Aptos framework itself is based on an autonomous account at 0x1 and other system addresses. Okay, I mentioned that an important objective for us is to make the blockchain agile, so to make it living, to make it able to evolve. No? And for us, it was important because of this to enable code upgrade. And first, in order to understand code upgrade, you need to understand how we actually deploy code in Aptos. So in the original DM move, we had like a deployment model where you deploy module by module. We have basically replaced this by a package-based model, which is also the way how you know when you work with Move, you have this package system, you have Move packages. So it's quite natural. It's a bit like a crate in Rust or so. A package just contains a set of Move modules, and if you publish it, you publish the package as a whole. And those modules inside of the package are all at the same address, so you need a signer for this address to publish it. But now the point is when you publish a module, you can mark it as either upgradable or immutable. And if a package is marked as upgradable, then you can replace it by a new package which passes compatibility checks. And we come back in a second what this means. That is, by the way, enabled again by the strongly typed Move bytecode and Move metadata, which is available in the bytecode, that we can actually check for compatibility. But before I go there, there is also the other kind of package which is immutable, which you find in the EVM space and elsewhere. And I want to be very clear, we warn actually users to be very careful if they use upgradable packages. So they might want, some users may want to use immutable. If you're actually going to use upgradable package, you should be probably use some autonomous approach for your signing off, whether the upgrade is allowed and not just a single key, because indeed there is a compatibility check, but even compatible upgraded code can be malicious and suddenly start stealing money. So you need to be sure that the upgrade is totally protected before you use that as a feature in your contracts. But you can do it. No? And as said, so the compatibility is enabled by the Move bytecode and by the type system. So what it basically means, you cannot add fields to existing resources. You cannot remove resources and re-add them, because that would allow you to fake the type. And let's say you remove a resource at address FF, and then you later add that resource with another type at the same address. Now you may have still in storage the old thing, and suddenly you are able to reinterpret a type with some other type, which I come back in the safety context, very, very dangerous. You don't want to do that. And all those things are cared for in upgradability. All those things are checked the compatibility. Also, whether all functions are still there and have the same signature. So basically in the upgrade scenario, you can add new functions and you can add new resources. You would, by the way, implement dynamic fields in classic Move by just adding a new resource, which is pretty much the same thing. So you have a resource R, which has a couple of fields. Now you want to add a new field, then you just add another resource R prime, which contains this new field and lives side by side with the other resource. That's a traditional way how to do that. Yeah, so there is another important aspect. Aptos ensures that if a package is immutable, then also all dependencies are immutable. So this kind of policy of package upgrade is basically transitively expanded to all the dependency of a package. And that sounds right now trivial because we have only upgradable, immutable as policies, but we are planning to have more different and finer-grained forms of upgradability down the road. And then that will be very important that you can guarantee the same policy for upgradability also for dependencies. There's one important exception which enables us that we can update actually the standard library and the Aptos framework. The Aptos frameworks, which include the move standard library, can always be upgraded by chain governance vote because otherwise we couldn't fix bad bugs on chain. No? Also, one other thing which I need to make clear. So in this world of upgrades, there is really only one version of a package on the chain at the same time, and everybody calling into that same version. If you want to create a new version, then you would today do that by naming your package. Now you have basically package underline v1, package underline v2. You can declare them as immutable or upgradable. That depends on your application. And this way you can actually store multiple potentially incompatible versions of the same product on chain. But with the same name, there is basically there's no different versions of the same named package on chain at one time, which simplifies this model significantly. Okay, so this is a slide I got from my colleague Aline about cryptography, and I don't really understand what's in the slide. I can just recommend you to read it. So we have a lot of different cryptographic primitives in the library. So we are trying to capture everything which might be needed for your purposes when you develop on Move. We also have some rather interesting upcoming things which I mentioned here, including zero-knowledge range proof verification and Patterson commitments. And I don't really know what that is, or only roughly, and I don't want to spend too much time on it, but that's an important aspect of our Aptos Move. Now, let me talk a bit more about governance. I think on Aptos blockchain governance. So I already explained parts of it, but let me point out some more details. So what does it mean if we, or what the governance actually governs on Aptos? No? So let's suppose we have some parameters on the blockchain, and these parameters include a lot of things. It can be the duration of an epoch. It can be the gas schedule which we are changing. It can be some other system parameters, a large set of parameters. That's definitely a change to the configuration of the blockchain. And how do we implement this? We do using scripts like I discussed before, which contain those updates to the settings of the blockchain. And then the Aptos community votes whether this script is okay. And this script is basically turned into a so-called on-chain proposal. And that on-chain proposal is voted on. And only if this vote succeeds, then this on-chain proposal can actually be executed. That follows from the logic how these scripts are implemented. The technical details are not that important here, but it's a nice model where you basically have inside of the script in move code the operation which the Aptos operators and community vote on, and they can see what is happening, and then you can execute it later. This also applies not only to blockchain parameters, but it also applies to code upgrades of the core frameworks. So if the core frameworks are upgraded, then that also is encoded in a script proposal, which, by the way, means indirectly that we actually have a programmatical code upgrade, no? Because the script contains some section where it actually runs some code upgrade, and that is by calling some arbitrary transaction. It's not longer the case like in classical moves that code upgrade is a particular module bundle kind of transaction or so. It's actually a regular transaction which we have defined somewhere in the framework, which you can call programmatically. And one of those use cases where you call code upgrade programmatically is basically as part of this proposal execution. Yeah, when the voting is successful, the script will be executed. Actually, it would be better to say the script can be executed. The script has like a piece of line inside there, which makes sure that it can only succeed if that particular script has been approved by governance. Okay, so that's how this part works. I want to jump a little bit in the standard libraries, if you have a little bit time here, and give you an idea what is there. So we do use the move documentation generator, which was created at DM times. So you probably, if you know a little bit on move, you know about the move standard library, which has been shrunken over time. Like Sam also knows, we have put a lot of things actually out of this library because we really want to have it containing only those things which are independent of any blockchain or Poly model on top of move. So there are strings, vectors, options, and this very basic types. Because this is now really restricted to move standard library, we have on top of it the Aptos standard library. And let's take a look what we have there. So I don't know, maybe this is a little bit too small. Maybe make it a little bit bigger. Yeah, so we have a couple of types here. So we can maybe start here. So we have some of those crypto functions which I mentioned. So are here available. Some of them have native implementations. Some of them have, I think, actually implementations that move. Now you see that the documentation generator allows us to do showing actually also the implementation and also navigating to other parts, to basically following the links. So that's actually, I didn't want it to go back. Let me go back here again. So this is about the Aptos standard library, Aptos hash. There are other interesting types, like, for example, we have an any type, which allows you to pack any type you want into some non-polymorphic, non-parameterized type, and then extract it back if you know the type. This is actually safe and works because of properties of compatibility of data structures, because once there is a data structure on chain, then for all times it can never change the data layout. And this any type, if you know a little bit of Rust or C++, is indeed also there. So it's a standard technique how you add polymorphism to strongly or statically typed language like move. Let's see, I can go back here. Okay. What's this? Okay. Aptos framework contains now a couple of more types, as you see here. So we have indeed account abstraction, we have a special version of accounts, we have coins, we have blocks, chain IDs, chain status, which are for the organization of the blockchain itself. We have this code module, which I mentioned, which basically allows you to upgrade code by calling the function ending here, initialize public fund publish package, no? Which you can call from anywhere in your transactions. And now let me go back. And then finally we have the Aptos token library, which is a framework for dealing with tokens and NFTs, which is still evolving at this point of time. Okay, we hear, by the way, more about Aptos tokens by a talk by Bo, in I think it's tomorrow, and we'll see some more details there. Okay, further topics I want to capture. First, I want to talk about language evolution. This is something we are very often asked. So I said initially that Move is a very simple language, and that is by design. However, I think the Move designers agree at this point of time that maybe some things are a little bit too simple and add a few more nice things to the language, syntactically, basically, but also some conceptual things which are missing. And I just want to give a heads up that this is
Hi, Wolfgang. You are muted again. Hi, Wolfgang, I cannot hear you.
Why don't you tell me that I'm muted?
Okay.
How long am I muted? Okay.
Yeah, all secure.
For how long am I muted? Okay. Anyway,
This is right.
just now. Okay, cool. Okay, so yeah, we are extending the language as part of this Move Language Partner Team meetings. No? So there is a set of issues on GitHub where you can see what we have discussed and what is agreed upon. And I just mentioned here some things which are agreed or mostly agreed upon. For example, we have more number types, no? So which people really ask for. We did not introduce signed integers because we don't like them. But if you want those, please push on us, and maybe we do it later. We have some syntax improvements planned. You can imagine, particular with this object style, which SWI has, but also in the way how we do classic move. So it would be really nice if you have this receiver.call notation. So if you have a function which works specifically for a particular struct or object, then you can use that call instead of having the receiver as a parameter to this function. So this is mostly approved, and we just need to design it. The problem is mostly for this kind of thing is not really that we have disagreement about whether it should be going to the language, but we need the resources and the time to implement it and carefully think about all the design implications. Another idea which we're having, if you actually use classic move, there's borrow global mute, and they sound like a little bit awkward. No? So you may want to have perhaps a notation like this, where you use the resource type, and then you give the address here because it's like an indexing, and then you give ampersand here to say that you want to have a reference. No? Similar in Aptos move, we have also a couple of things which we want to improve. Users are strongly asking us for being able to pass structures as parameters, and we are looking at this, and we will do it eventually. But it's not trivial because some people think it's trivial, but the problem is really in the modular encapsulation, which we discussed before. If you want to add structures to transactions, you need to avoid that someone can fabricate via these transactions values of the structures which should not be able to create over the module's API. But via deserialization, you could create theoretically everything. So you need to think about how this can be prevented, no? And we have some ideas here, and this will come very soon. Okay. Another aspect I want to bring up is tools we are working on, and that is indeed an ever-growing set of tools. Some of them come from Deem, some of them are new. So indeed the Move unit testing framework, which we are adapting for Aptos. We probably will have to adapt it even more than we're doing right now in order to make information like which is in the blockchain, like chain ID and other stuff, actually available to code, so they can test this blockchain specific scenarios, which isn't that trivial. We do have, as you know, I'm one of the main authors of the Move prover together with Mang Shu and others. The Move prover, which we're adapting right now for Aptos. We also have specified parts of the Aptos framework. We are not done with this work. There is more to do. There is also some additions to the Move prover which need to be done. We will hear more about the Move prover with 2 talks after this talk, I think. One from Mang Shu and one from Shudang. And yeah, so that's a great thing, which we are very interested in caring for. We have the Move package system, which is adapted for Aptos. So there are some things in the Move package system for Aptos, which are not in the base system. We have Move documentation generator, which we have seen in action. We have, which I didn't mention here, a pretty nice plugin created by a partner of us, Pontem, for IntelliJ, which is based on the Aptos compiler or the Aptos instance of the Move compiler. So this, by the way, this plugin for IntelliJ also allows auto formatting at this point of time. Maybe not in the most smartest way you can imagine, but at least in some basic way, and allows you all kind of things like, I think the SWI and Misten has something similar for VS Code, navigating around in your code, clicking at go to definition and find all usages and all this kind of things which you're used to. And I think if I mention this one, this is really a beautiful example of the power of having a community around Move. No? So this, SWE basically creates this plugin for VS Code, and we create a plugin for IntelliJ or our partners. Okay, so I'm coming to the end. Was the noise indicating that I should hurry up? Okay. So last two slides here. So Aptos Move Safety. Yeah. Okay. Move Safety. So Move Safety, I mentioned that is indeed absolutely essential. No? So there are two major concerns around Move Safety, at least. No? The one is type safety. I mentioned this already. So type safety means that you take some representation memory and suddenly interpret as another type. Let's say you have a structure which contains an address, and now you reinterpret, and then you have a signer of this address, and you can basically do whatever you want with the account. So that's very, very dangerous and leads to loss of assets. That's basically the biggest attack which can happen on a move-based blockchain. And the other thing is crashes, where you basically, the problem is, one contract crashes on one validator, then it crashes on all the other validators as well, because execution is deterministic, and therefore the entire blockchain goes down and basically is dead. No? And these are the two problems which are most burning. And we invested quite a lot of work and also resources in terms of money in trying to deal with that. We have external auditing by Certic and others. There are reports about this. We have we had an extensive internal auditing, which is supported by the Move community. Everybody worked on this. Wisten worked on this. Starcoin worked on that, and also MoveBit helped with this. So this was a great thing, where we all read again the important code, and we did actually not find very many bugs. And we have a bug bounty. And I didn't mention that, I forgot to mention, we are starting to set up continuous fuzzing of important components of the chain. During the bug bounty, just to be clear, there were bugs that were discovered, which were paid for dearly, but all these bugs were fortunately before we launched, and we feel now relatively safe about this. There is more about this to say in Ranshin's talk. We will in particular mention what we call a paranoid mode, which goes even further in our concerns around safety. We believe that what we have been doing here for Move is beneficial for the entire Move community. It's just coming on us because we are the first ones here, a part of Starcoin, but the first ones in the US, which go basically public with the mainnet. Okay, I come to the conclusions. Just an interesting comparison between different approaches here. And I have not SWE on here, but I mentioned SWE anyway. You will see in a second. So let's talk about a few aspects of comparing those blockchains. So when it comes to data storage, it's stored with the owner's account. That is an important property. That's how Move was originally designed and differentiated from EVM. In Solana, it's kind of not the case. So you have an owner's account, but it's associated with the program or the contract. No? In EVM, we know stored within the account, associated with a smart contract. So there is no differentiation between the smart contract and the data ownership. If it comes to parallelization, which is an important aspect, we are doing it by inferring parallelization at runtime via software transactional memory. In Solana, parallelization is achieved by specifying for the transaction what kind of data it's going to access. And that is my understanding is also what happens in SWE today. This is indeed in a certain way for the tooling very powerful, but maybe for the program model a little bit more restrictive. So I heard from Sen's talks, they are thinking about also some speculative, optimistic execution, parallel execution here, which I think is essential. From my point of view, it's essential because you want to do as much as you can on chain. But if you have to declare data dependency ahead of time of a transaction, how do you compute that dependencies if these dependencies actually depend on chain state? No? So what happens in order to do that, you have to execute now things outside of chain. it's a little bit like what you have seen, what got very elegantly in the examples you have seen at SAM. My criticism would be, yes, that looks very elegantly, but the price you have to pay for that is that some of the work, which you don't see and move anymore, now happens off-chain, and it's not really gone. The work is still there. No? That's what I would say anyway. If you compare it with EVM, nothing. No? It's only serial. There is no way happening there. And then last not least, that's pretty important, static dispatch. No? So we also understand that we may need some forms of dynamic dispatch. We're still thinking for compositionality of contracts, but right now this is default, and that enables a lot of things in analysis, verification, and safety of the blockchain. Okay, take a look at aptosfoundation.org if you want to know more about us, and there's also a link to the white paper. You can also directly jump into the developer side. And for generic move, I think the best reference we still have is the move book, which you'll find here, which is developed also in the move repo together with the other move stakeholders. Okay, so that's it for my part, and thank you very much for giving me the opportunity to talk here today.
Thank you, Wolfgang. There are some questions on the textbooks. Do you like answer or just reply on the textbooks?
A textbook?
The text chat. Yeah.
I'm sorry. I think you're combining my bad hearing, so I have a really bad. Maybe you can write it somewhere.
Okay, you can reply the question on the chat box. Yeah.
Chat box.
Yeah, the bottom is.
I see the chat box. Yeah, I see the chat box. There's another chat box. Okay.
Yeah. Okay.
Where's the other chat box? Let me stop we don't need the slide anymore, no? So I'm stopping this now. Then I have to see the controls better.
Okay. You can reply.
It's a special to check the module source code stored in an account. Yes, so it's actually even more like this. So when we deploy a package, I didn't mention that, we actually deploy the source code as well. And so the entire metadata, so basically the code as package metadata contains the source code and the ABIs and other information about the package, and this is all stored on chain in the same account where the code is also stored. There is an interesting question here, though, which we currently don't do. So in the way how you deploy via our tooling, there is a guarantee that the source, which you find on chain, is actually matching the bytecode, which is also on chain. But someone could send a malicious code upgrade transaction which is trying to fake this. And for that one, I think, yeah, we have actually a CLI command to verify that that when you basically download the source and compile it, that's actually the same bytecode, then it's actually on chain. But you have to manually do this verification step.